Can light die? It's a stupid question with a terrifying answer. And you'll understand why photons are the closest thing to immortal gods that physics allows, and why they survived billions of years of cosmic violence. If you're curious about the universe, make sure to subscribe to the channel. It helps us keep bringing you the latest discoveries from the edge of science. Now let's begin. Photons are strange. They're not like us. They don't age, they don't decay, they don't experience time the way we do. In fact, from a photon's perspective, if it even has one, its journey across the universe happens in literally zero time. The moment it's born is the same moment it arrives at its destination, whether that's your eye or a telescope mirror 13 billion light years away, but physics is always more complicated than it first appears. And when you start asking whether light can truly live forever, you open up a cascade of questions that lead us to the cosmic microwave background, to the limits of our telescopes, to the very edge of what we can know about the universe. Let's start with the basics. What exactly is a photon? A photon is a quantum of electromagnetic radiation. That's fancy physics speak for saying it's the smallest possible packet of light. It has no mass, no electric charge, and it always travels at the speed of light in a vacuum, approximately 300,000 kilometers per second. Nothing in the universe moves faster. Now here's where it gets fascinating. Because photons have no mass, they don't experience time. This isn't science fiction. This comes directly from Einstein's theory of special relativity. When you move faster, time slows down for you relative to someone standing still. At the speed of light, time dilation becomes infinite. Time stops. Imagine you're a photon born in the core of a distant star. From your perspective, your entire existence, your journey across billions of light years of space, happens instantaneously. You don't age because you don't experience duration. You exist in a timeless state. But from our perspective, watching from Earth, that same photon has been traveling for eons. We see it crossing space year after year, century after century. We can track its journey, measure its wavelength, detect its energy. So which perspective is correct? Both. That's the beautiful weirdness of relativity. Now you might be thinking, if photons don't experience time, doesn't that automatically mean they live forever? Well, not necessarily. And this is where modern physics gets really interesting. You see, living forever and not experiencing time are two different concepts. A photon might not age, but it can still be destroyed. It can be absorbed by an atom, giving up its energy to boost an electron to a higher orbital. It can collide with matter and cease to exist. It can be converted into other particles under the right conditions. But here's the deeper question, the one that physicists have been investigating for decades. Can a photon decay on its own? Can it spontaneously transform into something else, even in the emptiness of space, with nothing around to interact with? According to the standard model of particle physics, our best current theory of how the universe works at the quantum level, photons are absolutely stable. They cannot decay. They have no mechanism by which they can transform into other particles. They should theoretically exist forever unless something absorbs or scatters them. But the standard model isn't complete. We know this because it doesn't explain dark matter, it doesn't explain dark energy, and it doesn't fully reconcile with gravity. So physicists keep testing its predictions, pushing at its boundaries, looking for cracks, and one way to test whether photons are truly stable is to look for evidence of photon decay. If photons could decay, even with an extraordinarily long lifetime, we might be able to detect it. Several research teams have investigated this question using one of the most remarkable sources of ancient light in the universe, the cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light we can see. It's a faint glow of radiation that fills the entire universe, coming at us from every direction. This light was released approximately 380,000 years after the Big Bang, about 13.8 billion years ago. Back then, the universe was much smaller, much hotter, much denser. It was a seething plasma of protons, electrons, and photons, all packed together so tightly that light couldn't travel freely. Photons would scatter off electrons almost immediately, like trying to shine a flashlight through fog. But as the universe expanded, it cooled, and when the temperature dropped below about 3,000 degrees Kelvin, something remarkable happened. Protons and electrons combined to form the first neutral hydrogen atoms. Suddenly, photons could travel freely. The fog cleared. The universe became transparent. Those photons have been traveling ever since. They've crossed the expanding universe for over 13 billion years, and because of that expansion, their wavelength has been stretched. What started as visible and infrared light has been redshifted into the microwave part of the spectrum. When we detect the CMB today, we're seeing light that has been on a journey longer than the age of our planet, longer than the age of our sun, longer than the age of our entire galaxy. These are the oldest photons we have access to. If any light in the universe were going to show signs of decay or instability, it would be these photons. They've had 13 billion years to fall apart. So what do we see when we measure them? The CMB has been studied in exquisite detail by several space missions. The Cosmic Background Explorer, or COBE, launched by NASA in 1989, first mapped the temperature variations in the CMB. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, created an even more detailed map. And the European Space Agency's Planck satellite, which operated from 2009 to 2013, gave us the most precise measurements yet. All of these missions found the same thing. The CMB has an almost perfect blackbody spectrum. This is exactly what we'd expect from the thermal radiation of the early universe, cooled and stretched by cosmic expansion. If photons were decaying, we'd see distortions in this spectrum. There would be missing energy at certain wavelengths or unexpected peaks and valleys. The beautiful, smooth curve would be disrupted. But it's not. The spectrum matches theoretical predictions with stunning precision. In 2013, physicist Julian Heek published a paper analyzing what the CMB tells us about photon stability. He calculated that if photons do have a finite lifetime, it must be extraordinarily long. For a photon with a wavelength in the visible range, the lifetime would have to be at least 10 to the 18th years. That's a billion years, or about 100 million times the current age of the universe. Think about that for a moment. The universe itself is only about 13.8 billion years old. If photons can decay, their lifetime is so long that essentially none of them have decayed yet, not in all the time since the Big Bang. This is one of the most stringent limits we've ever placed on the stability of any particle. It tells us that photons are, for all practical purposes, immortal. But Heek's analysis revealed something else interesting. For photons to decay, they would need to have a tiny, tiny mass. Not zero, but close to it. Something on the order of 10 to the minus 54 kilograms or less. Wait a minute. Don't photons have zero mass? Isn't that one of the fundamental properties we just talked about? Well, yes and no. According to the Standard Model, photons are exactly massless. But if physics beyond the Standard Model exists, and most physicists believe it does, then it's conceivable that photons could have an incredibly small mass that we haven't detected yet. But if the photon mass is at that upper limit, and if photons can decay, then they would decay into even lighter particles. The only particles we know of that are lighter are neutrinos. Neutrinos are ghostly, nearly massless particles that barely interact with anything. Trillions of them pass through your body every second without you noticing. If a photon decayed into neutrinos, it would happen so slowly, so rarely, that we'd need to observe an enormous number of photons over a very long time to have any chance of detecting it. And that's exactly what the cosmic microwave background gives us. There are approximately 400 photons from the CMB in every cubic centimeter of space. They fill the universe, and they've been traveling for over 13 billion years. If we're going to catch photon decay in action, this is our best shot. So far, we haven't seen it. The CMB remains pristine, its spectrum undisturbed. Either photons are truly immortal, or they live so long that the difference doesn't matter. But let's step back and ask a different question. Even if photons don't decay, even if they're fundamentally stable particles that could exist for eternity, what actually happens to them as the universe evolves? Where do ancient photons go? What's their fate? This is where cosmology gets both beautiful and a little melancholy. Every photon in the universe is on a journey. Some were created yesterday when you turned on your phone screen. Some were created billions of years ago in the nuclear furnaces of long-dead stars. And some, like the CMB photons we just talked about, have been traveling since the universe was in its infancy. These ancient photons tell us stories. They carry information about the conditions in the early universe, about the first stars and galaxies, about cosmic events that happened before Earth even existed. When NASA's James Webb Space Telescope looks out into deep space, it's essentially a time machine. It's collecting photons that began their journey billions of years ago. The farther away an object is, the longer its light has been traveling, and the further back in time we're seeing. In July 2022, Webb captured what's called the first deep field image. It shows thousands of galaxies, some of which existed just a few 100 million years after the Big Bang. The light from those galaxies has been traveling for over 13 billion years to reach us. Think about the journey those photons took. They were created in massive young stars, blasting through stellar atmospheres, crossing intergalactic space, dodging clouds of gas and dust, surfing the expansion of space itself. And then after all that time, after all that distance, they happened to arrive at exactly the right moment when a 21.4-foot mirror was pointing in their direction, ready to catch them. It's humbling, isn't it? Each photon in that image is a messenger from the ancient past. And we just happen to be here now with the technology to receive that message. But here's something that might surprise you. Those photons didn't just travel through space. They traveled through expanding space. And that expansion changed them in a fundamental way. When a photon travels through expanding space, its wavelength gets stretched. This is called cosmological redshift. A photon that starts out as blue light might arrive as red light, or infrared, or even microwave radiation, depending on how far it's traveled and how much the universe has expanded during its journey. This isn't the same as the Doppler shift you experience when an ambulance drives past you, and the pitch of the siren changes. This is space itself stretching, and the photon stretching along with it. The CMB is the ultimate example of this. Those photons started out in the visible and near-infrared part of the spectrum. The universe at recombination, the moment when atoms first formed and photons could travel freely, had a temperature of about 3000 Kelvin. That's roughly the temperature of a red-hot piece of metal. But over 13 billion years of cosmic expansion, those photons have been stretched by a factor of about 1,100. Their wavelength is now 1,100 times longer. Their energy is 1,100 times lower. And the temperature of the CMB today is just 2.7 Kelvin, barely above absolute zero. Those photons haven't changed internally, they haven't aged or decayed. But the universe around them has changed and they've been transformed in the process. So even though photons might be immortal, they're not unchanging. The cosmos shapes them, stretches them, cools them, They carry the signature of cosmic history in their wavelengths. Now let's talk about another fascinating population of ancient photons, Starlight from the first stars. The very first stars in the universe, what astronomers call population 3 stars, formed roughly 100 to 200 million years after the Big Bang. These stars were very different from our Sun. They were made almost entirely of hydrogen and helium because heavier elements didn't exist yet. They had to be created later through nuclear fusion inside stars. Population 3 stars were probably massive, perhaps 50 to 100 times the mass of our Sun, and because they were so massive, they burned hot and bright and died young, exploding as supernovae after just a few million years. No population 3 star exists today. They all died billions of years ago, but the photons they created are still out there, still traveling through space. Some of those photons have been absorbed by dust and gas, some have been scattered by intervening matter. But some are still freely propagating, carrying information about the universe's first light show. The James Webb Space Telescope was specifically designed to find and study these ancient photons. Its infrared instruments can detect light from the earliest galaxies, including light that might have been produced by population 3 stars. In 2023 and 2024, Webb has been discovering galaxies that existed just 300 to 400 million years after the Big Bang. Some of these galaxies appear surprisingly bright and mature for their age, challenging our models of how quickly galaxies could form. These observations rely entirely on photons that have been traveling for over 13 billion years. Photons that witnessed the cosmic dawn, the epoch when the first stars ignited and began transforming the universe from a dark, neutral expanse into the bright, ionized cosmos we see today. Every one of those photons is a time capsule. And the fact that they've survived their journey, that they haven't been absorbed or scattered or lost, is itself remarkable. But not all photons are so lucky. Most photons created in the universe do eventually get absorbed. They hit an atom, transfer their energy, and cease to exist as photons. Their energy doesn't disappear. That would violate conservation of energy, but they do transform into something else: heat, kinetic energy, chemical energy, mass, through the famous equation E equals mc squared. This is actually how most photons die, if we can call it that. They don't decay, they interact. Consider photons from our own Sun. The Sun produces about 4 times 10 to the 26th watts of power, all in the form of electromagnetic radiation, mostly photons. These photons stream out in all directions. A tiny fraction of them hit Earth, warming our planet, driving photosynthesis, creating weather patterns, illuminating our days. When sunlight hits your skin, those photons are absorbed by molecules in your cells. The energy is converted to heat, which is why you feel warm. The photons themselves are gone. They've completed their journey. They were born in the Sun's core, struggled outward through hundreds of thousands of kilometers of dense solar material, taking perhaps 100,000 years to reach the surface, shot across 150 million kilometers of space in just 8 minutes and 19 seconds, and then ended their existence in your skin. From your perspective, that's a long journey. From the photon's perspective, it happened in an instant. Most photons in the universe have similar fates. They're created in some energetic process: a star, a quasar, a radioactive decay, a matter-antimatter annihilation, and then they travel until they hit something and get absorbed. But some photons, the lucky ones, the ones born in just the right place and traveling in just the right direction, can journey for billions of years without encountering anything. These are the photons we see from distant galaxies. These are the photons that make astronomy possible. And here's something beautiful to think about. Right now, at this very moment, there are photons from our Sun, from our planet, from human civilization, beginning their own journeys into deep space. Some of them will travel for millions or billions of years. Some might never encounter another particle. Some might be the light by which a distant civilization in the far future discovers that Earth once existed. In 1977, NASA launched the Voyager 1 spacecraft. It carries a golden record, a collection of sounds and images representing Earth and humanity. But long before that record reaches another star, if it ever does, photons from Earth will have already spread news of our existence across the galaxy. Every television broadcast, every radio transmission, every camera flash creates photons that escape into space. They're weak, they're scattered, but they're there, carrying information about us into the cosmos. Right now, about 79 light-years away, there's a sphere of radio waves containing the very first television broadcasts from the late 1920s and early 1930s. About 50 light-years out, there's the first episode of Doctor Who. About 43 light-years out, there's the moon landing. About 30 light-years out, there's the fall of the Berlin Wall. These are our messages in bottles cast into the cosmic ocean, and unless something absorbs them, they'll keep traveling, potentially forever. This brings us to a profound question about the distant future of the universe. What happens to all the photons when the stars die out? Current cosmological models suggest that the universe will continue expanding forever. It won't collapse back in on itself, and as it expands, it will cool. Stars will eventually burn out. Galaxies will drift apart. After an extraordinarily long time, perhaps 10 to the 100 years, even black holes will evaporate through Hawking radiation. What's left at that point? A universe that's cold, dark, and diffuse. But it won't be entirely empty. It will be filled with photons, all those ancient photons from dead stars, from the CMB, from evaporated black holes. They'll still be there. They'll have been redshifted to longer and longer wavelengths, lower and lower energies. Eventually, they might have wavelengths longer than the observable universe itself, but they'll still exist in principle. This is sometimes called the heat death of the universe, a state of maximum entropy where no more energy can be extracted to do useful work. Everything is in thermal equilibrium. Everything is the same temperature, just a tiny fraction above absolute zero. And floating through this dying cosmos will be countless photons, each one a ghost of the universe's energetic past. It's a melancholy vision, but there's something beautiful about it too. Even at the end of time, even when every star has died and every galaxy has faded, the light will remain, the photons will endure. But let's pull back from that distant, cold future and return to something we can actually study today. Because there's another population of ancient photons that's absolutely fascinating, and they're coming from some of the most extreme objects in the universe, quasars. Quasars are supermassive black holes actively feeding on matter. They're found at the centers of distant galaxies, and they're among the brightest objects in the cosmos. A single quasar can outshine an entire galaxy containing hundreds of billions of stars. The light from quasars has been traveling to us for billions of years. The most distant quasars we've detected formed when the universe was less than 1 billion years old. Their photons have been journeying through space for over 13 billion years. Now here's what makes quasar light especially interesting for our question about photon longevity. These photons have traveled through an enormous amount of intervening material. They've passed through clouds of gas, through the halos of galaxies, through regions where dark matter might be lurking. If photons could interact with dark matter, or if they could decay into dark matter particles, we might see evidence of it in quasar light. The photons might be dimmed or distorted in ways that can't be explained by normal absorption and scattering. Astronomers have studied this carefully. They've looked at the spectra of distant quasars, searching for any anomalies that might indicate photon decay or unexpected interactions. And what they found is, once again, that photons behave exactly as the standard model predicts. The light from quasars shows absorption lines where specific wavelengths have been absorbed by hydrogen, helium, and other elements in intervening clouds. This creates what's called the Lyman alpha forest, a series of absorption features that tell us about the distribution of matter between us and the quasar. But there are no mysterious disappearances of photons, no unexplained energy losses, no signs of decay. The photons that left those quasars billions of years ago have survived their epic journey intact. This gives us yet another confirmation that photons are stable over cosmological timescales. They can travel for the age of the universe without falling apart. But there's still more to this story, because while photons themselves might be immortal, the information they carry can be distorted, scrambled, or even lost. And that happens because of a phenomenon called gravitational lensing. Einstein's general theory of relativity tells us that massive objects warp space-time, and when light passes through warped space-time, its path bends. This is gravitational lensing, and it's one of the most spectacular confirmations of Einstein's theory. When light from a distant galaxy passes near a massive galaxy cluster between us and that distant galaxy, the cluster's gravity acts like a giant cosmic lens. It can magnify the distant galaxy, making it appear brighter. It can create multiple images of the same galaxy. It can even stretch the galaxy into arcs or rings. The James Webb Space Telescope has captured stunning images of gravitational lensing. Webb's first deep field shows numerous examples of lensed galaxies, their light bent and magnified by the gravity of the galaxy cluster in the foreground. Now think about what's happening to the photons in this process. They're not being absorbed or destroyed, they're not decaying, but their path through space is being altered. Two photons that left the same distant star at slightly different times and in slightly different directions might take very different paths around the lensing mass. One photon might take a shorter path, arriving years or even decades before its twin. Another might spiral around the lens multiple times before reaching us. This has led to some remarkable observations. In 2014, astronomers observed a supernova called supernova Refstal. The supernova was in a distant galaxy, and its light was being lensed by a massive galaxy cluster. The lensing created 4 distinct images of the supernova, each taking a slightly different path to Earth. Astronomers calculated that a 5th image should appear about a year later, as light taking a longer path around the cluster finally arrived. And in December 2015, right on schedule, the 5th image appeared. Think about those photons. They were all created in the same explosion, the death of a massive star 9.3 billion light-years away. But because of the geometry of space-time, some arrived a year before others. The photons themselves didn't change. They didn't slow down or speed up. But the fabric of the universe itself routed them along different paths. This tells us something profound. Photons are incredibly passive. They don't push back against the universe. They simply respond to the geometry of space-time, following what physicists call geodesics, the straightest possible paths through curved space. You and I, we experience gravity as a force. We feel Earth's gravity pulling us down. But photons don't experience it that way. From a photon's perspective, it's always traveling in a straight line. It's space itself that's curved. This is part of what makes photons such perfect messengers. They don't have agendas, they don't resist. They simply go where space-time tells them to go, preserving information about their origin for as long as they exist. Now let's talk about what happens to photons in the most extreme environments we know of, near black holes. Black holes are regions where gravity is so strong that not even light can escape. The boundary of a black hole, called the event horizon, is the point of no return. Any photon that crosses the event horizon is doomed. It will be pulled inexorably toward the singularity at the center, where our current theories of physics break down. But what happens to a photon as it approaches the event horizon? Does it experience something different from its usual timeless existence? This is where things get really weird. From the photon's perspective, nothing changes. It's still moving at the speed of light, still experiencing zero passage of time. It crosses the event horizon and continues inward. But from our perspective, watching from a safe distance, something strange happens. As the photon gets closer to the event horizon, the intense gravity causes extreme time dilation. We see the photon slowing down, its light becomes more and more redshifted, its energy draining away. In fact, from our perspective, the photon never quite reaches the event horizon. It appears to freeze just above it, becoming redder and dimmer, fading asymptotically toward invisibility. We never actually see it cross. This isn't an illusion. This is genuinely what we observe. The photon's journey to the event horizon takes an infinite amount of time from our frame of reference. But wait, didn't we just say that photons don't experience time? How can their journey take infinite time? This is the paradox of perspectives. From the photon's timeless viewpoint, it crosses immediately. From our time-bound viewpoint, it never crosses. Both are true. Both are valid descriptions of reality from different frames of reference. This is what happens when you push the laws of physics to their extremes. Intuition breaks down, common sense fails, and you're left with mathematical descriptions that work perfectly but sound like paradoxes when you try to translate them into everyday language. Stephen Hawking added another twist to the story of black holes and photons in 1974. He demonstrated that black holes aren't entirely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. The mechanism is subtle, but here's the basic idea. In quantum field theory, empty space isn't truly empty. It's filled with virtual particle-antiparticle pairs that constantly pop into existence and annihilate each other. Normally, these virtual particles exist for such a short time that we can't detect them directly. But near a black hole's event horizon, something remarkable can happen. A virtual pair might be created right at the edge of the event horizon. One particle falls in, crossing the point of no return. The other escapes. Because they can't recombine and annihilate, the escaped particle becomes real. It carries energy away from the black hole. From the outside, it looks like the black hole is emitting radiation. And since this radiation carries away energy, and energy is equivalent to mass, the black hole slowly evaporates. For large black holes, this process is incredibly slow. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate. That's far, far longer than the current age of the universe, but smaller black holes evaporate faster. A black hole with the mass of a mountain would evaporate in a time comparable to the age of the universe, and a microscopic black hole, if any exist, would explode in a burst of Hawking radiation almost instantly. Most of the Hawking radiation is in the form of photons, so in a sense black holes are photon factories. They're converting their mass into light, albeit very slowly for large black holes. This means that the ultimate fate of every black hole is to become a spray of photons and other particles. The black hole evaporates, and what's left is radiation spreading out into space. Those photons will join all the other ancient photons filling the cosmos, adding to the population of light that will outlive the stars themselves. Now here's a question that might be bothering you. If photons can be created from other forms of energy, and if they can be absorbed and transformed back into other forms of energy, are we really talking about the same photons? Is there continuity of identity? This is actually a deep question in quantum mechanics. Photons are indistinguishable. If I have two photons with the same wavelength, polarization, and direction of travel, there's no experiment I can do to tell them apart. They're fundamentally identical. In fact, quantum mechanics tells us that identity doesn't work the way we intuitively think it should for particles. When two electrons interact and then separate, you can't say which one is which. They lose their individual identities and become interchangeable. This is even more true for photons. A photon absorbed and a photon emitted, even if they have the same properties, aren't the same photon in any meaningful sense. Each absorption-emission event destroys one photon and creates another. So when we talk about ancient photons from the cosmic microwave background or from distant quasars, we're talking about photons that have traveled without being absorbed. They're the survivors, the ones that made it through billions of years of cosmic history without hitting anything, and that makes them even more special. Out of the countless photons created in the early universe, only a tiny fraction have survived to reach us. We're seeing the lucky ones, the ones whose paths happen to avoid all obstacles. Let's go deeper into the quantum weirdness of photons, because understanding whether light can exist forever requires us to grapple with some of the strangest aspects of reality. You see, photons aren't just little balls of light bouncing around. They're quantum objects, and that means they behave in ways that seem impossible according to our everyday experience. Take the famous double slit experiment. When you fire photons one at a time through two narrow slits, they create an interference pattern on a screen behind the slits. This pattern is what you'd expect if each photon somehow went through both slits simultaneously and interfered with itself. But if you try to measure which slit the photon went through, the interference pattern disappears. The photon suddenly behaves like it went through one slit or the other, not both. This isn't a limitation of our measurement technology. This is fundamental to how reality works at the quantum level. The act of observation changes what you observe. What does this have to do with photon longevity? Everything. Because it tells us that photons don't have definite properties until they interact with something. Until a photon is measured or absorbed, it exists in a quantum superposition, a combination of multiple possible states. An ancient photon from the cosmic microwave background, traveling for 13 billion years, hasn't had definite properties for that entire journey. Its polarization, its exact energy, even aspects of its path through space existed in quantum uncertainty until the moment it hit the detector on the Planck satellite, or the WMAP probe. From this perspective, asking whether a photon can exist forever is asking whether quantum information can persist indefinitely without decohering, without collapsing into a definite state. And the answer appears to be yes. As long as the photon doesn't interact with anything, its quantum state remains coherent. Time doesn't erode it, distance doesn't corrupt it. The quantum information is preserved. This has profound implications for understanding the universe. Every photon we detect from the early cosmos is delivering quantum information that has remained intact for over 13 billion years. It's a direct connection to the conditions of the early universe, preserved in the quantum state of light. But there's a catch. The universe isn't truly empty. Even the vacuum of space contains fields, virtual particles, and quantum fluctuations. Do these affect traveling photons? In normal circumstances, no. The vacuum is the lowest energy state of the quantum fields that fill space. Photons can travel through it without losing energy or changing their properties. But there are exceptions. In extremely strong electric or magnetic fields, the kind you might find near neutron stars or in the vicinity of black holes, something strange can happen. The vacuum itself can affect light. This phenomenon is called vacuum birefringence. The intense fields can temporarily create virtual electron-positron pairs from the quantum vacuum. These virtual particles interact with passing photons, slightly altering their polarization and speed. The effect is tiny, but it's real. And in 2017, a team of astronomers reported the first observational evidence of vacuum birefringence. They studied light from a neutron star called RxJ 1856.5-3754. The neutron star has a magnetic field about 400 trillion times stronger than Earth's. Light passing through the magnetized vacuum near this neutron star showed exactly the polarization signature predicted by quantum electrodynamics, the theory that describes how light and matter interact at the quantum level. This tells us that even empty space can affect photons, given extreme enough conditions. The vacuum isn't completely passive, it has structure, properties, quantum mechanical behaviors, but these effects are only significant in extraordinarily intense fields. For photons traveling through normal intergalactic space, the vacuum is essentially transparent. The photons pass through unaffected, preserving their properties across cosmic distances. Now let's talk about another quantum phenomenon that affects photons. Entanglement. Quantum entanglement is one of the most counterintuitive predictions of quantum mechanics. When two particles are entangled, they share a quantum state. Measuring one particle instantaneously affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, and he was deeply uncomfortable with it. But experiments have confirmed it repeatedly. Entanglement is real. Photons are particularly easy to entangle. When certain crystals are illuminated with laser light, they occasionally split one photon into two lower energy photons through a process called parametric down conversion. These two photons are entangled. Their polarizations are correlated in a way that can't be explained by any local hidden variable theory. Scientists have created entangled photons and separated them by hundreds of kilometers, sending one down fiber optic cables or even bouncing them off satellites. The entanglement persists, the quantum correlation remains intact. In 2017, China's Misha satellite successfully created entangled photons and distributed them to ground stations more than 1,200 kilometers apart. The entanglement survived the journey through space, through Earth's atmosphere, to detectors on the ground. This raises a fascinating question. Could photons remain entangled over cosmological distances? Could there be photons from the early universe that are still entangled with each other, separated now by billions of light years? Theoretically, yes. Entanglement doesn't decay with distance. As long as the photons don't interact with anything that destroys their quantum coherence, they should remain entangled no matter how far apart they travel. In practice, though, photons from the early universe have almost certainly interacted with something over their long journey. They've been scattered by electrons, deflected by gravitational fields, absorbed and re-emitted by atoms. These interactions would break any primordial entanglement. But the possibility is tantalizing. Somewhere in the universe there might be pairs of photons that have been entangled since the first moments after the Big Bang, still sharing their quantum state across the expanse of space. This brings us to another deep question about photon stability. What happens to a photon in an accelerating reference frame? According to general relativity and quantum field theory, observers in different states of motion see different things when they look at the vacuum. An observer at rest sees empty space, but an accelerating observer sees a thermal bath of particles popping out of the vacuum. This is called the Unruh effect. If you accelerate at a constant rate, you would detect radiation with a temperature proportional to your acceleration. The vacuum itself appears warm to you, even though it appears cold to someone who isn't accelerating. This effect is closely related to Hawking radiation from black holes. In fact, the two phenomena arise from the same underlying physics in quantum field theory. Now here's the weird part. This means that whether photons exist or not can depend on your state of motion. What one observer sees as empty space, another observer sees as filled with photons and other particles. This doesn't mean the photons aren't real. It means that the concept of particles is observer-dependent in quantum field theory. What's fundamental isn't the particles themselves, but the quantum fields that permeate space-time. For our question about photon longevity, this has a subtle implication. Photons aren't eternal objects with definite existence. They're excitations of the electromagnetic field, and whether those excitations exist, how many there are, and what their properties are, can depend on your frame of reference. In the reference frame of the photon itself, if such a frame even makes sense, the entire history of the universe is compressed into a single instant. The photon doesn't persist through time because it doesn't experience time. From our frame of reference, photons can travel for billions of years. But from their perspective, they exist in a timeless state where birth and death are the same moment. This is one of the profound mysteries at the heart of relativity and quantum mechanics. Time itself isn't absolute. It's relative to your motion and your gravitational environment. And for a particle moving at the speed of light, time stops entirely. Let's shift gears and talk about photons in a completely different context. Inside matter. When light travels through a transparent material like glass or water, it slows down. The speed of light in a medium is less than the speed of light in vacuum. This is why lenses can focus light and why objects appear distorted when you look at them through water. But what's actually happening to the photons? Are they moving more slowly? Not exactly. The photons themselves still travel at the speed of light. But as they move through the material, they're constantly being absorbed and re-emitted by atoms. Each absorption-emission event takes a tiny amount of time, and this delays the photon's overall progress. It's like walking through a crowded room. Your walking speed doesn't change, but you have to stop and navigate around people, so your overall progress is slower. But here's the crucial point. The photon that comes out the other side of the glass isn't the same photon that went in. The original photon was absorbed, a new photon was emitted. That photon was absorbed by another atom, another photon was emitted. This happened countless times as the light crossed the material. So when we ask if photons can exist forever, we have to be careful about what we mean by the same photon. Photons are constantly being created and destroyed. What persists isn't individual photons, but the electromagnetic field and the energy it carries. In the sun's core, photons are created by nuclear fusion reactions. These photons are high-energy gamma rays, but the sun's core is incredibly dense, and these photons can only travel a fraction of a millimeter before being absorbed by an atom. The atom re-emits a photon, often at a slightly lower energy. That photon travels another tiny distance before being absorbed again. This process repeats millions of times. It takes somewhere between 10,000 and 170,000 years for the energy from a fusion reaction in the sun's core to random walk its way to the surface. By the time it emerges, the original high-energy gamma ray has been transformed into thousands or millions of lower-energy photons, mostly in the visible and infrared parts of the spectrum. Not a single photon that reaches Earth from the sun is the same photon that was created in the fusion reaction. They've all been absorbed and re-emitted countless times. What travels from the sun to Earth is energy carried by generation after generation of photons. This might seem to undermine the idea of photon longevity. If photons are constantly being destroyed and recreated, can we really say they live forever? But remember, the photons we're interested in are the ones traveling through empty space, the ones that avoid absorption. Those photons, the cosmic wanderers, can indeed persist for the age of the universe. Now we need to confront one of the most mind-bending aspects of cosmology, the edge of the observable universe and what it means for ancient photons. The observable universe has a boundary, not because there's a wall or an edge to space itself, but because light has only had a finite amount of time to reach us since the Big Bang. We can only see objects whose light has had time to travel to Earth in the 13.8 billion years since the universe began. But here's where it gets complicated. Because the universe has been expanding this whole time, Objects that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light-years. When we account for cosmic expansion, the current distance to the edge of the observable universe is about 46.5 billion light-years in every direction. The total diameter of the observable universe is roughly 93 billion light-years. This means there are photons reaching us right now that have been traveling for over 13 billion years, but the objects that emitted them are now separated from us by more than 46 billion light-years. Space itself has expanded during the photon's journey. Think about what this means for the photon. It's been traveling at the speed of light the entire time, never slowing down, never speeding up. But the destination has been moving away the whole time, carried by the expansion of space. It's like running on a treadmill that's accelerating. You're running as fast as you can, but the finish line keeps getting farther away. For photons from very distant objects, this creates a strange situation. They're heading toward us, making progress, getting closer. But the space between us and their origin point is expanding faster than they can close the distance. Some regions of space are so far away that light leaving them now will never reach us, no matter how long we wait. The expansion of space is too fast. These regions are beyond what's called our cosmic event horizon. And here's the unsettling part. As the universe continues to expand and the expansion accelerates due to dark energy, more and more galaxies will cross this event horizon. Galaxies that we can see today will eventually become invisible, not because they've died or dimmed, but because the space between us is expanding so rapidly that their light can no longer reach us. The photons from those galaxies will keep traveling toward us, forever making progress, but never arriving. They'll be trapped in expanding space, eternally journeying toward a destination they can never reach. In a sense, these photons will exist forever, but they'll be causally disconnected from us. They're in a part of the universe that is permanently separated from our part. This raises a philosophical question. If a photon exists but can never interact with anything, can never be detected, can never deliver its information, does it really exist in any meaningful sense? Physics doesn't have a clear answer to this. It's outside the domain of what we can measure or observe. But it highlights the strange nature of photon existence in an expanding universe. Now let's talk about the cosmic horizon problem and how it relates to photon travel time. When we look at the cosmic microwave background, we're seeing light from regions of space that are now on opposite sides of the observable universe. These regions are separated by more than 90 billion light-years today. But here's the puzzle. When that light was emitted, those regions had never been in contact with each other. They were too far apart, and the universe was too young for light to have traveled between them. Yet the temperature of the CMB is remarkably uniform across the entire sky. Regions that have never communicated with each other have almost exactly the same temperature, to within 1 part in 100,000. How did they coordinate to have the same temperature if they've never been in causal contact? This is called the horizon problem, and it's one of the major puzzles that led to the theory of cosmic inflation. Inflation proposes that in the first fraction of a second after the Big Bang, specifically from about 10 to the minus 36 seconds to about 10 to the minus 32 seconds, the universe underwent a period of exponentially rapid expansion. It grew by a factor of at least 10 to the 26 in that tiny interval. Before inflation, all the regions we can see today were close together in thermal equilibrium. They all had the same temperature because they were in contact, exchanging energy and photons. Then inflation happened, stretching them apart faster than light could travel between them. The photons that were moving between these regions got stretched out too, their wavelengths expanding along with space. When inflation ended, the universe continued to expand, but at a much slower rate. Eventually, photons could travel significant distances again, and when recombination happened at 380,000 years after the Big Bang, photons were released from all these regions, carrying information about their temperature. Those photons have been traveling ever since. And because all those regions started with the same temperature before inflation separated them, the CMB appears uniform across the sky. So in a very real sense, the uniformity of the cosmic microwave background is evidence of photons that existed before, during, and after inflation. They carried information through the most dramatic expansion event in cosmic history. This tells us something remarkable about photon resilience. Even when space itself is expanding exponentially, stretching at speeds far exceeding the speed of light, photons preserve their quantum information. Their wavelengths stretch, their energies drop, but the information they carry remains intact. Now let's address an even deeper mystery, the black hole information paradox and what it means for photon information. When matter falls into a black hole, it carries information with it. The information about its quantum state, its composition, its history. According to classical general relativity, that information crosses the event horizon and is lost forever. But quantum mechanics has a fundamental principle. Information cannot be destroyed. Quantum processes are reversible, at least in principle. If you know the final state of a system precisely enough, you should be able to calculate its initial state. These two principles seem to contradict each other when applied to black holes. This is the information paradox. Stephen Hawking initially argued that information is indeed destroyed by black holes, violating quantum mechanics. But in 2004, he conceded that he was wrong. The information must somehow be preserved, even though we don't yet fully understand the mechanism. The current leading idea is that information is encoded in the Hawking radiation that black holes emit. As a black hole evaporates, it releases photons and other particles. These particles are entangled with each other in incredibly complex ways, and the pattern of entanglement encodes all the information about everything that ever fell into the black hole. If this is correct, then photons play a crucial role in preserving information across the most extreme event in physics, the complete evaporation of a black hole. A black hole forms, matter falls in. Information appears to be lost. But over an inconceivably long time, the black hole evaporates into Hawking radiation, and the photons and other particles in that radiation carry all the information back out. The information never truly disappeared. It was scrambled, encoded in quantum correlations, hidden in the entanglement structure of the radiation. But it survived. This suggests that photons are not just passive carriers of energy. They're carriers of information, and that information is protected by the fundamental laws of quantum mechanics. Even when photons are absorbed, the information they carried isn't destroyed, it's transferred to the absorbing system. The information is preserved even if the photon itself ceases to exist. This leads us to think about photons in a new way. Maybe the question isn't whether individual photons can exist forever, but whether the information they carry is eternal. And from that perspective, the answer is yes. Information cannot be destroyed. It can be scrambled, hidden, encoded in complex quantum states, but the laws of physics forbid its destruction. Every photon from the cosmic microwave background carries information about the conditions in the early universe. That information has been preserved for 13 billion years. And if those photons are eventually absorbed by some distant civilization's telescope, the information will be transferred to that telescope's detector, then to their computers, then to their understanding of the cosmos. The information doesn't die, it just changes form. Let's shift perspective and talk about photons at the smallest scales, in the realm of quantum field theory. At the quantum level, a photon isn't really a particle in the classical sense. It's a quantized excitation of the electromagnetic field. The field itself is fundamental. The photon is what happens when that field has one quantum of energy above its ground state. This might seem like splitting hairs, but it has important implications. The electromagnetic field exists everywhere in space-time. It's always there, even in empty space. A photon is just a ripple in that field, a wave of energy propagating through it. When we ask if photons can exist forever, we're really asking if these ripples can persist indefinitely without dissipating. In classical physics, waves in most mediums do dissipate. Sound waves fade as their energy is absorbed by the air. Water waves die down as their energy is transferred to friction and viscosity. But electromagnetic waves in a vacuum have no medium to absorb them. There's no friction, no viscosity, no mechanism for dissipation. The electromagnetic field itself is what's waving, and it does so without losing energy. This is why photons are stable. The electromagnetic field doesn't have anywhere for the energy to go. It can't radiate that energy away because photons are the radiation. Unless some new physics beyond the standard model provides a decay channel, some way for the electromagnetic field to transfer its energy to another field, photons should persist indefinitely. And so far, despite decades of searching, we haven't found any evidence for such a decay channel. Experiments have looked for photon decay in numerous ways. They've searched for gamma rays that might come from photon decay in cosmic voids. They've analyzed the spectrum of the CMB for distortions. They've studied light from distant quasars for any signs of energy loss beyond what's expected from cosmic expansion. All of these searches have come up empty. Photons appear to be perfectly stable within the limits of our ability to measure. The most recent constraints published in the last few years pushed the lower limit on photon lifetime to such extraordinary values that for all practical purposes we can say photons are immortal. But science never stops asking questions. There are theoretical frameworks beyond the standard model where photons might have incredibly small masses and correspondingly long but finite lifetimes. Some extensions of the standard model propose that photons might have an extraordinarily tiny mass. We're not talking about the mass of an electron or even a neutrino. We're talking about a mass so small that it might be 10 to the minus 54 kilograms or less. That's a decimal point followed by 53 zeros and then a number. Why would physicists even consider this possibility? Because certain theories that attempt to unify all the forces of nature, or that try to explain dark matter and dark energy, predict that photons might acquire a tiny mass through subtle quantum effects. If photons have mass, even an infinitesimal one, the consequences would be profound. Massive photons would behave slightly differently from massless ones. They would travel slightly slower than the speed of light in a vacuum. They could decay given enough time. And the electromagnetic force, which extends infinitely in our current understanding, would have a finite range. Astronomers have tested this possibility by making incredibly precise measurements of magnetic fields around planets and stars. If photons were massive, electromagnetic forces would weaken over very long distances in a way that's different from what we observe. Jupiter's magnetic field extends millions of kilometers into space. The solar wind carries magnetic fields throughout the solar system. Galaxies have magnetic fields that span hundreds of thousands of light years. All of these observations are consistent with photons being exactly massless. If photons had even the tiniest mass, these large-scale magnetic fields would behave differently. The current experimental limit based on measurements of planetary magnetic fields and galactic magnetic fields puts the upper limit on photon mass at less than 10 to the minus 54 kilograms. That's about 10 to the minus 18 electron volts if we use the units particle physicists prefer. To put this in perspective, if the photon had that much mass, its Compton wavelength would be about 100,000 trillion kilometers. That's larger than the entire Milky Way galaxy. So even if photons have mass, it's so ridiculously small that for all practical purposes they behave as if they're massless, and they would still persist for timescales far exceeding the age of the universe. But let's push even further into speculative territory. What does string theory have to say about photons? String theory proposes that fundamental particles aren't point-like objects, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. The photon, in string theory, is the vibration pattern of a closed string in its lowest energy state. In most formulations of string theory, photons remain massless and stable, but some versions of string theory, particularly those that try to explain cosmic acceleration and dark energy, predict subtle modifications to electromagnetism at very large scales. These modifications might cause photons to interact weakly with dark energy or with extra dimensions of space that are curled up too small for us to detect directly. Such interactions could, in principle, cause photons to lose energy over cosmic distances in ways that aren't explained by standard cosmology. Astronomers have searched for these effects. They've looked at the spectra of distant supernovae, which serve as standard candles for measuring cosmic distances. If photons were losing energy through interactions with dark energy or extra dimensions, the supernovae would appear dimmer than expected in a way that's different from the dimming caused by cosmic expansion. So far, the data is consistent with photons behaving exactly as standard physics predicts. There's no evidence for exotic energy loss, but string theory makes another intriguing prediction about photon behavior at the absolute highest energies. At energies approaching the Planck scale, which is about 10 to the 19 billion electron volts, quantum gravitational effects become important. Space-time itself becomes foamy and uncertain. The smooth geometry of general relativity breaks down, and we need a quantum theory of gravity to describe what happens. String theory is one candidate for such a theory. It predicts that at these extreme energies, photons might behave differently. Their speed might depend slightly on their energy. Higher energy photons might travel slightly faster or slower than lower energy ones. This would violate a fundamental principle of relativity, that the speed of light in a vacuum is constant for all observers and for all photon energies. If this effect exists, it's incredibly tiny, but it might be detectable by studying gamma-ray bursts, the most energetic explosions in the universe. Gamma-ray bursts occur when massive stars collapse into black holes or when neutron stars collide. They release enormous amounts of energy in seconds, creating photons with energies ranging from radio waves to ultra-high energy gamma rays. Some gamma-ray bursts are billions of light-years away. Photons from these bursts travel for billions of years before reaching us. If their speed depends on their energy, even by a tiny amount, the highest energy photons should arrive at slightly different times than the lower energy ones. Several space missions have searched for this effect. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, has observed hundreds of gamma-ray bursts at various distances. Scientists have analyzed the arrival times of photons with different energies from these bursts, looking for energy-dependent delays. The results so far show no significant energy-dependent speed variations. Photons of all energies, from those with energies of a few 100,000 electron volts to those with energies exceeding 100 billion electron volts, arrive at the same time within the precision of the measurements. This puts strong constraints on quantum gravity theories, including many formulations of string theory. Whatever the ultimate theory of quantum gravity turns out to be, it must preserve the constancy of light speed to extraordinary precision. This tells us that photons, even at the highest energies we can observe, behave as stable, massless particles that travel at exactly the speed of light. Their journey across billions of light-years doesn't reveal any exotic physics, at least not at the level we can currently measure. Now let's talk about loop quantum gravity, another candidate for a quantum theory of gravity. Loop quantum gravity takes a different approach from string theory. Instead of proposing that particles are strings, it suggests that space-time itself is quantized. Space and time aren't smooth and continuous at the smallest scales. They're made of discrete, indivisible chunks like pixels on a screen. The smallest meaningful length in loop quantum gravity is the Planck length, about 10 to the minus 35 meters. The smallest meaningful time is the Planck time, about 10 to the minus 44 seconds. At these scales, space-time has a granular structure. It's woven from quantum loops interconnected in a complex network that gives rise to the smooth space-time we experience at larger scales. What does this mean for photons? If space-time is quantized, then photons traveling through it might interact with this granular structure. It would be like light traveling through a medium with a very fine texture. Some formulations of loop quantum gravity predict that this could cause high-energy photons to travel slightly slower than low-energy photons. The effect would be extraordinarily tiny, but it might accumulate over cosmic distances. Again, observations of gamma-ray bursts provide a test, and again, the results show no evidence for this effect. Photons of all energies arrive simultaneously, suggesting that if space-time is quantized, the scale of that quantization must be smaller than even the Planck length, or the interaction between photons and the quantized structure is even weaker than predicted. These null results are actually important. They're telling us that whatever the correct quantum theory of gravity is, it must preserve the classical behavior of light to incredible precision across cosmic distances and energies. Photons are remarkable in their consistency. Whether they're low-energy radio waves or ultra-high-energy gamma rays, whether they've traveled for a nanosecond or 13 billion years, they behave exactly as Maxwell's equations and Einstein's relativity predict. This consistency is one of the pillars of modern physics. It's what allows us to trust our observations of the distant universe. It's what makes cosmology possible as a quantitative science. Now let's consider what the next generation of observatories might tell us about ancient photons. The James Webb Space Telescope is currently the most powerful infrared observatory ever built. It's already revolutionizing our understanding of the early universe. But even more capable instruments are in development. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will have a field of view 100 times larger than Hubble's. It will survey huge swaths of the sky, finding millions of distant galaxies and mapping the distribution of dark matter through gravitational lensing. The photons that Roman will collect include some of the oldest light in the universe, from galaxies that formed just a few 100 million years after the Big Bang. Each of those photons has been traveling for over 13 billion years, carrying pristine information about cosmic dawn. On the ground, the next generation of extremely large telescopes is under construction. The Extremely Large Telescope in Chile, with a primary mirror 39 meters in diameter, will collect more light than all existing large telescopes combined. These telescopes will be able to study the spectra of extremely distant objects in unprecedented detail. They'll analyze the light from the first stars and galaxies, looking for chemical signatures that tell us about the conditions in the early universe. Every spectrum they capture will be built from individual photons, ancient travelers that have crossed cosmic voids to deliver their messages to our detectors. There are also missions planned to study the cosmic microwave background with even greater precision than Planck. These missions aim to detect the faint imprint of primordial gravitational waves on the CMB polarization, a signature of the inflationary epoch that would confirm our understanding of the first moments after the Big Bang. If successful, these observations would be analyzing photons that not only survived for 13 billion years, but also carry information about the universe when it was less than a trillionth of a second old. Think about that chain of information preservation. Conditions during inflation at 10 to the minus 36 seconds after the Big Bang imprinted patterns on spacetime. Those patterns affected the plasma of the early universe. The patterns were transferred to the photons released at recombination. Those photons traveled for 13 billion years, and now they're being detected by satellites and telescopes, revealing secrets from the very beginning of time. Let's dive into some of the most extreme environments where physicists create and study photons, particle accelerators. At facilities like CERN's Large Hadron Collider, protons are accelerated to 99.9999991% of the speed of light, and then smashed together with tremendous energy. In these collisions, the proton's kinetic energy is converted into a shower of particles, including vast numbers of photons. Some of these photons have energies far exceeding anything found naturally on Earth. They're high-energy gamma rays, each carrying as much energy as a macroscopic object like a flying mosquito, but concentrated in a single quantum particle. These ultra-high-energy photons exist for only fleeting moments before they interact with matter or convert into particle-antiparticle pairs. But during their brief existence, they're real photons, indistinguishable in principle from the low-energy photons of radio waves, except for their enormous energy. What's fascinating is that these photons obey exactly the same physics as their low-energy cousins. They travel at the speed of light. They have the same relationship between energy and frequency. They interact with charged particles through the same electromagnetic force. This universality is remarkable. Photons spanning more than 20 orders of magnitude in energy, from radio waves at 10 to the -9 electron volts to the highest energy gamma rays at 10 to the 11 electron volts, all follow the same rules. This tells us something profound. The photon is a truly fundamental particle. It doesn't have substructure that reveals itself at different energies. It doesn't change its nature. A photon is a photon, whether it's ancient starlight or a gamma ray from a particle collision. But there's an energy limit even for photons traveling through space. It's called the Greisen-Zatsepin-Kuzmin limit, or GZK limit, and it arises from the interaction between ultra-high energy photons and the cosmic microwave background. Here's how it works. The cosmic microwave background fills all of space with photons. These are low-energy photons with energies around 6 × 10 to the -4 electron volts. They're everywhere, remnants from recombination. Now imagine a photon with extremely high energy, say 10 to the 20 electron volts, traveling through space. From this photon's reference frame, the CMB photons are blue-shifted to much higher energies due to the Doppler effect. Eventually, if the high-energy photon is energetic enough, the CMB photons appear to have enough energy that when the high-energy photon collides with one, they can produce an electron-positron pair. This process, called pair production, removes energy from the high-energy photon. If the photon starts with energy above about 10 to the 19 electron volts, it will quickly lose energy through repeated interactions with CMB photons. This means there's a practical upper limit to the energy of photons that can travel long distances through the universe. Above the GZK limit, photons degrade rapidly, their energy cascading down through pair production events. Cosmic ray observatories have confirmed this effect. The highest energy cosmic rays, which are mostly protons rather than photons, show a cutoff at energies consistent with the GZK limit. Photons at these energies are even more strongly affected. So while photons can exist at arbitrarily high energies when they're created, those that travel cosmic distances are limited to energies below the GZK threshold. The CMB acts as a cosmic fog that blocks ultra-high energy photons from distant sources. This is actually a fascinating example of photons regulating photons. The ancient cold photons of the CMB prevent young, hot photons from traveling too far. It's a kind of cosmic speed limit enforcement, where the enforcers are themselves the thing they're limiting. Now let's talk about photons in extreme states of matter, starting with something called a Quark-Gluon Plasma. In the first microseconds after the Big Bang, the universe was so hot and dense that protons and neutrons couldn't exist. Instead, matter existed as a soup of free quarks and gluons, the fundamental constituents of nuclear matter. Physicists have recreated this state of matter in heavy ion collisions at accelerators like the relativistic Heavy Ion Collider and the Large Hadron Collider. When gold nuclei or lead nuclei are smashed together at near-light speed, they create a tiny fireball of quark-gluon plasma that exists for only 10 to the minus 23 seconds before cooling and condensing into normal particles. This plasma is extraordinarily hot, over 4 trillion degrees Celsius, far hotter than the core of any star, and it's opaque to photons. In fact, one of the ways physicists study quark-gluon plasma is by looking at how it absorbs and scatters photons. Photons created inside the plasma have to fight their way out, interacting with the churning sea of quarks and gluons. Some photons are absorbed and re-emitted many times before escaping. Others convert into quark-antiquark pairs, then reform. The photons that finally emerge carry information about the plasma's properties. This is similar to what happens inside the Sun, but far more extreme. The quark-gluon plasma is denser and hotter than the solar core by many orders of magnitude. Yet even in this environment, photons follow the same fundamental rules. They're still excitations of the electromagnetic field. They still travel at the speed of light between interactions. They still preserve quantum information through the chaos. When the plasma cools and condenses into hadrons, the photons that escape carry a record of conditions inside that tiny, ephemeral fireball. They're messengers from a state of matter that hasn't existed naturally in the universe since the first microseconds after the Big Bang. Now let's consider photons in another exotic state, Bose-Einstein condensates. At temperatures within a few billionths of a degree above absolute zero, certain atoms can enter a quantum state where they all occupy the same quantum state. They become indistinguishable, behaving as a single quantum entity. This is a Bose-Einstein condensate, and it's one of the coldest and most quantum states of matter we can create. Photons, being bosons like the atoms in these condensates, can in principle form photon Bose-Einstein condensates. And in 2010, physicists at the University of Bonn succeeded in creating one. They filled a tiny cavity with dye molecules and cooled it to room temperature, then pumped it with laser light. The photons bounced back and forth between mirrors interacting with the dye molecules. These interactions allowed the photons to reach thermal equilibrium and cool down to a very low effective temperature. At a critical point, the photons suddenly condensed into a single quantum state. They all had the same frequency, the same polarization, the same direction of travel. They became a superphoton, a macroscopic quantum object made of light. This photon condensate behaved like a bizarre form of laser light, but with completely different physics. In a normal laser, the photons are stimulated to emit coherently by an external pumping mechanism. In the photon condensate, coherence emerges spontaneously from the quantum statistics of bosons at low temperature. What does this tell us about photon longevity? It shows that photons can exist in collective quantum states that span many individual photons. The distinction between one photon and another becomes meaningless in the condensate. In a sense, the condensate is both one photon and many photons simultaneously. It's a macroscopic manifestation of quantum mechanics, and it demonstrates that photon identity is fluid and context-dependent. When you think about the cosmic microwave background filling all of space, you might wonder if it's something like a photon Bose-Einstein condensate. After all, these photons all originated from the same thermal source. They've been traveling for billions of years, and they fill the universe uniformly. But the CMB isn't a condensate. The photons have a wide range of energies and directions, following a thermal distribution. They're not all in the same quantum state. They're incoherent, random, like the light from an incandescent bulb rather than a laser. Still, the CMB represents the largest collection of photons we know of, roughly 400 billion photons per cubic meter, filling all of observable space. That's about 10 to the 88 photons in total. These photons collectively carry information about the entire observable universe at recombination. Each photon is a tiny piece of that cosmic puzzle, and they've all been traveling for 13 billion years, preserving their information. Let's shift our perspective to the deep future. What will happen to all these photons as the universe continues to expand and evolve? Current cosmological models suggest that the expansion of the universe is accelerating, driven by dark energy. This acceleration means that the universe will continue to expand forever, becoming ever more empty and cold. As stars exhaust their fuel and die, fewer new photons will be created. The last stars will burn out in about 100 trillion years. After that, no new Starlight will illuminate the cosmos. But the photons that already exist will continue traveling. The CMB will become even more redshifted, its temperature dropping toward absolute zero, but never quite reaching it. In about 10 to the 100 years, black holes will have evaporated through Hawking radiation, releasing their mass as photons and other particles. The universe will be filled with an incredibly dilute gas of photons, neutrinos, electrons, and positrons, all spreading ever farther apart as space expands. Eventually, even these particles will be separated by distances larger than the current observable universe. A photon created in the last gasp of a black hole's evaporation might travel for 10 to the 100 years or more without encountering anything. These photons will exist in a universe that's essentially empty, cold, and dark. Yet they'll still exist, still traveling at the speed of light through expanding space, still carrying energy and momentum. From the photon's timeless perspective, none of this matters. Whether it travels for a second or 10 to the 100 years, it experiences no duration. Its existence is a single eternal moment. But from our perspective, these future photons represent the ultimate in longevity. They will outlast stars, galaxies, even black holes. They will be the last remnants of a universe that once was filled with light and life and complexity. Can photons exist forever? In practice, no individual photon will. The universe is too full of stuff for any photon to avoid interaction indefinitely. But in principle, photons are among the most stable entities in the universe. They don't decay, they don't age, they don't wear out. In that sense, photons are eternal, not because they last forever, but because they exist beyond the very concept of lasting. They simply are, unchanging and timeless, the universe's most fundamental messengers, carrying information across the void, connecting all things, making the cosmos knowable. And every time you see light, from the sun, from a star, from a candle flame, you're witnessing this timeless phenomenon, this quantum miracle that has endured since the beginning of time, precisely because, from its own perspective, time doesn't exist at all.